Hey everyone, thanks for all joining the workshop here with Pi Squared to learn about the upcoming USL transceiver, which is an amazing piece of technology that the guys will get into in a sec. But I'm just going to give a very quick intro on why it matters. So let's talk about interoperability. Cross-chain communication is key. Also, clicker communication is important as well. Let's do it like that. What's the state of interop today? Okay, so we have disparate networks. We have multiple runtimes, dozens of runtimes, hundreds of chains, roll-ups, everything. How do we make sense of it all? We don't have the exact answer actually today, but what we do have is distribution frameworks that are based on systems that have been built up over the last few years. We've got V1s, V2s, and we're coming into V3s as we change out and work on new verification mechanisms that will enable seamless communication between these networks. So it's really important that these networks can talk to each other and understand each other, but also be able to trust each other, obviously, securely at the end of the day. And what's driving us to build something new? Well, we see the need for people, chains, protocols, integrators themselves to be able to have the choice to choose between their security models, trade-offs between speed, cost, and performance, and different types of security guarantees at the end of the day. This is what's going to enable us to scale, making sense of all of this and abstracting it away, making it seamless. So we know that cross-chain messaging operates at massive scale today. There's tens of billions of messages going through across the entire interop space. So we know that it's important. We have product market fit. And we see that cross-chain messaging is also really secure today. I looked online. There's over 60 audits that have been done across the top interop protocols, highest bug bounties. It's a honeypot as well for security risk. So it's really mission critical today that we make sure that we have these secure methods of being able to verify cross-chain messages. And it's everywhere. It's used in every use case. You have to be natively multi-chain today. If you go out, you need liquidity, you need tokens, you need interoperable frameworks as well. So how do we make this better, basically? So we came out with our native token transfer framework where we basically separated the messaging layer from the verification layer for our token transfer messaging. It came out about 6 months ago. It secures $55.5 billion in value today under these contracts across chains, across all EVM and Solana today. And we call it a framework because it's not a standard. It's completely open. And the idea is that anyone can build on it and build a verification mechanism. They can build an interop bridge, a cross-chain communication system. This is the idea of it today. And we use Wormhole as a platform and the Guardian network as a basis for trust to enable these new verification mechanisms to proliferate. And we offer a distribution platform for this. So we have different models of how this works with the tokens. It's configurable, it's ownable, you get great security, you get all the bits and pieces. We thought about this in depth. You get rate limiting, you get accounting, there's no lock-in, and there's threshold attestations, which is critical as well. So you can set up your messaging transceivers to set up M of N threshold verifications. You can do 1 of 1, 2 of 2. You can integrate the Pi Squared transceiver in conjunction with the Wormhole transceiver today in a 2 of 2 threshold setup. And you get the full power of the stack here as well. So again, you get vertically integrated front ends, while you don't have to then worry about the verification mechanisms. So we have a full-on ecosystem. It's growing today, and this is what I wanted to show you guys. This is how it works. When a message is emitted to the entity manager, it will then deploy an event to burn message, whatever you need to share, basically to your transceivers. They will then emit that message out to your network, your verification network. This is in Wormhole's case how it works. The Pi Squared team is going to show you how their transceiver works as well today. And then this can verify. You can use the Pi Squared setup by itself You can add this in as well for extra security. If you're already integrated with Wormhole, that's great. You can add the Pi² transceiver in today, and you can unlock the power of formal verification in your verification for cross-chain messaging. So without further ado, I'll hand it over to the Pi² team. This is an amazing piece of technology. I'm super excited to see this. So let's give it up for the boys.
Yep. Hello. Yep. Thank you, Uzi, for the very nice and warm introduction. Thank you. So hello, everyone. I'm Xiaohong Chen. I'm the CTO of Pi². And joining us today are our chief architect, Yi Zhang, and our blockchain developer, Chenlong Ma. So I'm very happy to be here, right, to talk about Pi², its mission and goals, and also our universal settlement layer and its integration with the Wormhole's native transfer token framework. And so we have a 30-minute presentation ahead, and I think I'd like to use the first 20 minutes to go over Pi²'s big vision and mission. It probably has a different taste, right, from the second part where we'll be showing you a concrete demo of the universal settlement layer. So we do have some time at the end for questions, but if you have any questions during the presentation, please interrupt me at any time. So I'm very open for discussion with you. Okay. All right. So Pi² is unique as the world's first modular universal protocol. And this protocol offers 3 highly valuable benefits. So the first is that you can program in any programming language. And second, you can settle any type of proof, including zero-knowledge proofs. And third, you can reach lightning-fast generalized consensus. Okay, so these are the 3 main benefits that Pi² tech stack offers you. So let's explore these points a bit further. First, you can program in any language. So that means that Web3 application and smart contracts can be written in any programming language, even your custom language, right? So you are not restricted to learning particular Web3 applications simply because only they are compatible with a blockchain ecosystem. And Pi² is universal in that sense, right? It brings all the Web2 languages to the Web3 world. Second, you can settle any type of proof, including zero-knowledge proof. So all the data and computation and transactions can be consistently represented, stored, verified, settled, and used. And it's really up to the users and applications to decide what proof mechanism they like to use, right? So and there are a lot of options out there, from the classic mathematical proofs to the new emergent zero-knowledge proofs to digital signatures or to simply validation by re-execution. All these proof mechanisms are out there freely to be chosen depending on your needs. And Pi² is not specific, right, to a proof mechanism. It's compatible with all of them. And finally, you can reach lightning-fast generalized consensus. So as you may know, traditional blockchain requires a very strong, strict property where you have to reach a total ordering of your past transactions, right? And that's actually what limits the speed and scalability of blockchain. Well, so what Pi² enables is a more generalized consensus model, which can give you better scalability. The market opportunity for Pi² is massive because it enables any developer, it doesn't matter what programming language you like, right? So any developer to build for any blockchain. So take Ethereum, for example, right? So the developer base for Ethereum is basically centered around Solidity developers, which is about like 8,000. And if we zoom out a bit and you look at the Web3 developers in general, so according to public data source, the number is about 26,000, right? But Pi² in contrast is not limited to a particular programming language because it is universal. So our vision is actually to engage a much larger potential developer base, including those who are familiar with programming in, say, C, Rust, Python, and so on. right? And over time, we look forward to bring all the Web2 developers, even prompt engineers, to the Web3 world, so we can allow for an unprecedented growth in the Web3 ecosystem. So how do we achieve this? So we achieve this via 3 core major innovations, and they are orthogonal to each other, right? So the first one is the ULM, or the Universal Language Machine. So it allows to write smart contracts in any programming language, including your custom language. You can bring your own language to the blockchain, to the ecosystem. And currently we support EVM, Solidity, Wasm, and Rust, but we'll soon support more. So that's the first component. It's not going to be the main topic for today's presentation, but we do have another workshop on Thursday, which will be focused on the ULM. So feel free to check it out if you're interested. The second tech stack is the USL, or the Universal Settlement Layer, which will be the main topic for today. It's about proofs, right? So you can generate proofs of execution and settle them on a common layer across ecosystems and applications. And currently we support both mathematical proofs and zero-knowledge proofs. We'll be talking about the performance as well here later in the talk. And the last piece is a universal consensus. As we said, it enables a more generalized consensus model, which gives you better scalability. But this is another topic, not for today. Leave it for future. So I want to mention, so as you can see here, the keyword here is the universal, right? The universality. So I think the question here is not really why. I think we all agree that universality is a great feature to have. Right? I want to embrace all developers, in the ecosystem. So I think the question is really the opposite. Why don't we have it yet? Why is a problem? Why not? And one of the reasons is that programming languages create barriers. Right, it's the same as like in human language. Like I believe many of you are like me, where English is not our native language. So in order to like communicate, right, in a great event like DEVCON here, we need to pick up a language and be proficient in it. And you can imagine how many developers, talented developers, are at least marginalized or effectively excluded from this community if they're not proficient in English. The same thing happens here in programming language. So we have all these languages, C, Java, Python, classic Web2 languages, EVM, Solidity, these emerging blockchain languages. And for each of them, we develop tools, right? Some tools you are more familiar with, like interpreters, compilers. You use them all, every time, all the time, right? Use them to execute programs and so on. But sometimes you want to prove that your smart contracts are correct, there are no bugs, and then you use more advanced tools like formal verification tools and so on. The bottom line here is that we have all these languages, and we have to develop for each of them all the tools, right? So if we have L languages and T tools, we end up with L times T systems to maintain. So this causes language barriers. It takes time to develop tools for the new emerging languages. You have to take effort to maintain and update them as the language evolve. And of course, you have to train developers, right, for them to be proficient in those languages. And these huge barriers across ecosystems and applications are preventing us from having a universal solution in the blockchain ecosystem. And at PySquare, we want to break, this programming language barriers using formal semantics. Okay, and this is a new terminology, so let me explain a bit. So what is the formal semantics of a language? Okay, so it is a mathematical definition of your language. Okay, not only that, it is a mathematical definition that is 100% rigorous, no ambiguity, complete, and executable. So if you have the formal semantics of your language, then in theory, you have all the information you need to generate all the tools you want for that language. So that is the definition. And if we have a formal semantics, and internally we're using, you can define all these languages, the formal semantics of these languages, in what we call a universal language framework. And right now we're using a framework called K, but you can use other frameworks as well. There are many of them out there. But once you define them in the universal language framework, you automatically get all these tools from the semantics, right? So it's a separation of concern. We separate language design from tool implementation. Now you may ask, as a developer, how does it matter to me? Why does it matter? Well, imagine that you have your own application, and for some reason you want to develop it, you want to write it in your custom language, right? And one big concern when you want to do that is that you have to do, design and implement all these tools for your custom language from scratch. There's nothing really you can reuse. But if you have some sort of like a universal solution like this, you can really plug and play your language. All you need to do is sit down, write the formal semantics of your custom language, give it to the universal language framework, then you're good to go. You have all these languages tools available for you. Okay, so you can really plug and play your language. And because formal semantics is a rigorous mathematical definition of a language, all the tools here are correct by construction. So they naturally enable verifiable computing. And that's a very important piece of our tech stack, which I will go into next. So let me talk about pi squared, which means proof of proof. It is zero knowledge proof of mathematical proof. And it is a verifiable computing framework for all languages. Okay. And this is how it works. It's an entire workflow of proof. Let's go from the input. So what you have here is you have a programming language you want to work with. You have the program, say a smart contract for your application, and its associated execution environment. And then stuff happening. There's stuff going on, and eventually you get a ZK proof, a zero knowledge proof. So the very classical verifiable computing framework. You have your program executed in some execution environment, and at the end, you get a ZK proof for the execution. Okay. Let's then look a bit close into the workflow and see how is it different from the other verifiable computing framework. One of the biggest differences is that you see the programming language now becomes an input, right? In other words, it's not a verifiable computing framework for a particular language. No, it's a universal verifiable computing framework where you can instantiate it or you can give a programming language to it as input, right? If you're a Solidity developer, pass Solidity here. If you're a Python developer, you give a Python language definition here. It's exactly the same workflow. And then once you have a programming language, there's an automatic way to generate an interpreter from it, so you can execute programs. And then going through some more steps, we end up with a mathematical proof. So this mathematical proof verifies the computation of the program using the semantics. And what's happening here is that we reduce arbitrary computation to one type of computation, which is checking this mathematical proof is correct, right? And then we can implement this mathematical proof checker, which is a very tiny program. It checks whether the math proof is correct in any ZK VMs on the market, right? And then we can use that to generate a ZK proof. But you can see here, our approach here is compatible with any ZK technology because you can really implement the same checker in whatever ZK VMs you prefer. And I think, of course, this is very clear that this is an approach that gives you universality. Why? Because you have the entire programming language as input, right? There's nothing specific about the programming language, a particular programming language here. So I think the obvious, the elephant in the room here is the performance, right? So of course you can do things at the most generality, right? You can do things using mathematical definition, correct by construction and all that. But how about performance? Do you lose performance? So I think we like to, so that's the topic for the next few slides. So there are a couple of important intermediate steps here. So one is this interpreter, how fast it is compared to how fast it is, this interpreter compared to the state of the art. The second is the generation of mathematical proof. What is the overhead there? And the last one is on ZK. So let's look at them one by one. So we've done a lot of experiments, and we have some very interesting results. So this is probably one of the most important slides if you want to take back with something. So this is one of them. So semantic space execution is not just correct by construction. It's actually fast. Right. So let me pause here because this is very important because it's the first time in history that we observed this. Semantic space execution is not only correct by construction, but also faster. We've done many experiments. This is a typical one. So we take a test program, 1K swaps, simple test program that does 1,000 swaps, unit swap. And the first line is the baseline, right? So you compile it using the Solidity compiler, and then you execute using Geth. It takes 248 microseconds. So that's a baseline. Then what we do in the second line is that we take exactly the same program and give it to a Solidity semantics, right? So we define the semantics of Solidity and generate an interpreter automatically, okay? And we can use that interpreter, which is automatically generated from a mathematical definition of Solidity, and run exactly the test program. And we are only 5% slower. So the overhead there is only 5%. But you see, you already get correct by construction property here. And not to mention I could do verifiable computing and all that. And what's further interesting is that once you are in the mathematical domain, there are a huge amount of optimizations, which we call proof engineering, like find the right mathematical lemmas to shorten proofs and so on. And even by doing the very preliminary optimizations, we get 63% faster, right? So we take the program, the unit swap, and we optimize the semantics a bit, specialize to the unit swap smart contract. And we use the optimized semantics to run exactly the same program. The result is 63% faster. So again, I think this is the first time that we've seen that semantics-based execution, meaning that you don't write an interpreter, okay? You write a form of semantics and derive an interpreter automatically. It's faster than the mainstream execution. So I think this is probably one of the most promising results out there. It really shows that formal semantics-first approach is really feasible. All right, so once we have a form of semantics, we can generate mathematical proofs. There are a lot of things going on here. So this is semantics-based execution without any proof generation. We do that in 2 steps. So the proof things are sort of like a human-readable stuff, right? Includes information about what's actually going on in the semantics-based execution. Because there are a lot of things you have to serialize stuff. So we're looking at overhead from 6x to 10x. And then we can complete them by generating the final proofs in parallel. And in total, the overhead is around like 10x. And I would like to remind you that this is the result we observe for the over like a 4 to 5 month development, right? So from starting from scratch. So this is the result we have so far, and we obviously definitely look forward to improve the number here in the future. And finally, on the ZK side, as I said, one advantage of our approach is that we are compatible with any ZK VM. Right, so actually, we here we list a couple of a subset of those. Like we have RISC-0, JOT, SP1, and Kailo. We run them using the same the same mathematical proof, which has about 6,000 steps, and this is time that each of the ZK VM takes to generate the final ZK proof. And you can see that RISC-0 powered by the GPU is the fattest, followed by JOT and so on. I do want to say that we have a big disclaimers here, right? So it's a very non-trivial experiment to do. There are so many factors involved, and for example, I want to say that Kailo, right? They have various provers, and for now, the number we have here is based on one of their old provers. So we are working on to make their latest prover works. It's our fault. So take the numbers here as with a grain of salt, right? But I think the message here is that the performance here is okay, and we are compatible with any ZK VMs. It's not specific, right, to a particular proof mechanism. All right. So with all that said about formal semantics, about proof generation, so let's zoom in a bit and look at the USL, the Universal Settlement Layer. So what the USL is, or what makes the USL universal, is the concept of claims. Claims are anything provable. So it is this abstract mathematical object that can hold a statement about something. Okay, and it is that mathematical encoding which gives us the universality. Okay, and here are a couple of example statements you want to make, right, about a blockchain ecosystem that are claims. Okay, the first bullet point, we've seen that, right? Computation. Not a computation for Solidity, for EVM, but any computation. Computation in any programming language or VM. For example, you have a piece of code in whatever language you have, and you can make a statement, like given the pre-state or given this input, I execute this code, I get a post-state or this output. This triple becomes a claim, right? This triple is a claim. It is verifiable, or it can be proved, right? It's provable. So there are other statements about computation which doesn't change state, right? So for example, you have a big blockchain, you want to know what's the balance of some address, or can you have a view function over the state get some result? That's also a claim. If I run the state query function on some big state, get a result, well, it's a claim. And all these things can be verified through various means, proofs like mathematical proofs. We're seeing that, right now we have like a 10x overhead, or through ZK proofs in any approved ZK VM. We also saw that it's compatible with any ZK VM, or even through re-execution. Just re-execute them again, right? So all these are available. All these proof mechanisms are available. But there are more types of claims, right? So for example, consensus, right? You want to prove that a block belongs to the canonical chain. Again, that is a claim that can be stated as a mathematical statement and can be proved. And also you can have vetted knowledge or information, like someone puts the formal semantics of Solidity, right, at some address by some identity, right? So, definitions, oracles, identities, all these things like knowledge or information, they can also be verified, for example, using digital signatures, right? So the bottom line here is that this is what makes the USL, the Universal Settlement Layer, universal. It's the concept of claims, a mathematical object that captures the effect of making a statement of something. And different claims can have different means to be verified. But the point is you only need to verify them once, and then you can use them everywhere, right? And by everywhere, I mean really everywhere, like across ecosystems. And we'll see that in the next slide. So really the USL is a decentralized network of incentivized verifiers, like they accept claims and their proofs, and they validate claims or verify claims using the proofs, and the proofs can be provided by users, different applications. They can be generated by services, solvers, or even the USL verifiers themselves, right? And the claims, as we discussed, they are self-contained, right? So a claim has all the information you need to verify itself, right? So it doesn't depend on other claims. So what we really have here is a set of the verification points, not a list, not a sequence. And order of truth here is irrelevant. The claims can be independently verifiable, embarrassed in parallel, and it is what enabled the universal consensus. So once a claim is validated, they can be accumulated to the set of truth, right? The set of claims that have been validated, and that set is the USL state, right? And then as an application built on top of the USL, say you want to use a fact, right? So say some transaction happened on some other chain, and that claim, I can make a claim, and that claim can be verified and then added, right? Accumulated to the USL state. Now, as an application, I want to use that fact. I will need to check that that claim belongs to the USL states. I only need to do a membership proof, right? To prove that the claim of interest belongs to the set of claims that have been validated, right? And these membership proofs are very succinct and can be verified very efficiently. So we have some preliminary work with Pod on this. So basically, any USL-based chain services are expected to implement one function, verify membership, and it gives us universality. And this is how we achieve, verify once and use it everywhere across ecosystems. So next, I'll pass this on to my colleagues, Yi and Chenlong, and they will give you a concrete USL demo on bridges integrated with a wormhole NTT, and you can see how we can achieve interoperability and having a more interconnected, efficient, and very file secure blockchain infrastructure. So yeah, thank you.
Hello, everyone. Thanks, Xiaohong, for the introduction. So next, we will give you a demo of a simple bridge application that allows user to transfer tokens from Sepolia to Optimism Sepolia network. And before we actually dive into the demo, I'd like to give a very quick overview of the framework, so of the entity framework of Wormhole and how we integrate the USL with it. So this is a typical workflow. The highlight part is the typical workflow of the Wormhole, where the user interact with this entity manager contract, and under the hood, the Wormhole transceiver and Wormhole core contract kind of route the cross-chain messages through their Guardian network. Their Guardian network will attest the cross-chain messages and deliver to the destination chain. So in addition to that, the next slide. So user can also implement their own transceiver contract and route the message through the their own customized off-chain network, and they can apply their own attestation method in addition to the Wormhole default attestation method. So on the destination chain, the developer can configure to set a policy for a message to be accepted on the destination chain. For example, they can require a message to be attested by both off-chain network or either of them. So next slide. So we integrate the USL with the Wormhole entity framework by implementing our own transceiver, the USL transceiver, and we have the USL endpoint contract. So basically, we will store these cross-chain messages inside this USL endpoint contract and emit events. The events will trigger the off-chain claim generator to generate claims and proofs. So that is just described by Xiaohong. And we will show you the concrete, the information about this claim and proof in the demo. So don't worry about that. No. Go back. So, and then once the USL is verified the claim and proof, then this validated claim can be used at the destination chain. So this process can be done either manually or through some automatic relayer. So now I think you have some basic idea of how the whole things work, and then we can jump into the demo. So this is a very common bridge interface, and we already deployed all the contracts on Sepolia and Optimism Sepolia network, and also we pre-mint some tokens on Sepolia. Now let's just enter some token to transfer. Yeah. So you click the transfer buttons and approve the transactions. So then you can go to the history page. So basically in this page, it will list all the bridge transactions that are initiated by this account. So we have a few bridge transactions already done before the demo, but maybe we can first take a look at the contract. Yeah, so basically when the transfer function is actually delivered to the entity manager contract, it actually first burn the token. So yeah, and then it will construct entity message that specifies the amount of token to be minted on destination chain together with other meta information. And then this message will be stored in the USL contract in a public map called relays. So here I want to have a few words. Basically, we just store this message in the contract for this demo purpose. So in production, you may want to store this message in incremental incremental Merkle tree and only store the tree root in the contract in order to save gas and space. So and in the end, it will emit events, right? The events will trigger the off-chain our claim generator to generate claims. So please pay attention to this core data. That this is basically a core data to this relay public map, so that the claim generator can retrieve these cross-chain messages. So okay, let's go back to the demo. I think now the transaction is completed, and then we can click the view button to actually see the claim and proof. So we can decode the claim. So the basic claim is contains a few information. For example, the block number, the chain ID, and the core data that we just saw in the event. And then this is the output, which is the entity message, right? We can further decode it, and you can see in the payload, this specifies the amount of token that needs to be minted on the destination chain. So this is the claim part. And in order to verify such claim, right, there have multiple ways. As mentioned by Xiaohong, we can do check mathematical proof, or we can do ZK proofs. Here, we demonstrate a way to kind of proof by re-execution. So in these claims, it's just a series of Merkle inclusion proof of the storage keys that will be accessed by this view function. So the USL node will use this proof to load the partial state in a verifiable way and re-execute the view function on the state to check if the output matches. So I think I'd like to emphasize 2 points here. So first, the claim and proof, they are self-contained, so that the node of the USL doesn't need to rely on any other services. The second part is, so the proof is kind of minimal because we only construct partial state instead of the whole blockchain state. So that's why it makes the whole service scalable. So now I think the rest part, so now this proof is validated on the USL, and I think the rest is just to relay this validated proof to the destination chain in order to mint tokens, right? It can either be done manually or through some automatic relayer. So here we just complete the transaction manually and submit the proofs, submitted the claim and the inclusion proof that just Xiaohong explained to the destination chain. Once these set inclusion proof are checked, right, and then the corresponding tokens will be minted. So we can check in the destination chain. So the token is minted on the destination chain. Yeah. So I think this is the first half of the demo, where we show a successful workflow of our bridge application. And in the second part, I want to show you a scenario where our claim generator is done, right? So maybe we can do that. We stop the claim generator, and then we initiate the bridge transaction as we did in the first demo. Okay. Okay, now let's go to the history page and wait there for a bit, right? What we should expect. Because the claim generator is done, so no claim can be generated. And once this transaction, the bridge transaction is received, is confirmed on the source chain, right? Because no transaction, no claim are generated anymore. So basically, we're kind of stuck in this state, right? You can see the claim is setting forever. And at this stage, usually user need to wait for the developer to fix the issues and to resume the workflow. However, I think the nice thing about our architecture is that the whole workflow is actually by the proof and claim. It doesn't care who generates the claim or how the claim is generated. As long as the claim and proof can be verified by yourself, it is sufficient, right? So that means the user, instead of waiting for the developer to fix the issues for users, user can start the claim generator locally on their machine in manual mode, and they can generate the proof and the claims themselves. So let's do that. So as we can switch to the manual mode, the user can download the code to their local machine and start the service. It's very simple. And since it's no longer monitor all the events generated blockchain, so he needs to grab his bridge transaction hash and then submit to the local their local claim generate service. So, and then upon instant, then it's start to generate the claims and then submit to the USL for verification. Once it's complete, you see that we can complete the workflow as usual. I think this concludes our whole demo. Yeah, thank you. I will pass back to Xiaohong.
Thank you, E, for the demo. And I think we are on top of the time. So let me just wrap up. So basically, I think what we see here is a demo where there are many benefits here, but I think you can really see that because we focus on claims, and the claims are self-contained and they can be independently verified, right? So we can get some scalability. And as E said, it's not specific to any proof mechanism, right? So we have done some works on math proof generation and ZK proof generations in the demo. So for now, we just for simplicity, right? So we're using validation by re-execution, but there's right. So there's nothing specific, right? There's nothing in our infrastructure that's tied to a particular proof mechanism. It's really it's really compatible with any proof mechanism out there. I want to bring back to our vision, which is really to embrace, right, the very large potential developers out there in Web2 and bring them to the Web3 world. And so that's our mission, and that's why we focus so much on universality. And as I said, this is only, if you remember, the US is just one part of our module. So we are going to have another demo, another wonderful workshop on Thursday, talking about the universal language machine. And there you can also see that how we can use the language frameworks to enable, I would say, ultimate interoperability, right? You can write smart contracts in different programming languages, modifying the same state of the same blockchain, right? And yeah, so scan our QR code to follow us, on social media. These are, the next panel and the next workshop, right? So there's a workshop on Thursday, and I will wrap up here, and I'm very much looking forward to seeing you again on Thursday. Thank you.